Okay, so now we're going to solve a system of three equations that's not in triangular form using Gaussian elimination. Alright, and it's just elimination. It's just now you got more than two equations, but it's still the same idea. We're going to multiply one equation, or maybe two equations, by a constant to get opposite coefficients, add them together to eliminate a variable strategically. And by strategically, I mean we want to eliminate one variable at a time. Alright, so we can interchange rows. So like the top equation and bottom equation, we could switch them if we want. We can multiply any equation by a non-zero constant, and we can add multiples of one equations to the other equation. Alright, so with this one, so we already have z eliminated in this second equation. So you might want to multiply everything in this top equation by -5 and everything in the bottom equation by 3, and we can eliminate z. That would be one way to do it. Okay. We can also try to eliminate our x's since we already have opposite coefficients here, and then we could just double this second equation and add it to the bottom equation. Alright, so that's what I'm going to do, but just eliminate one variable at a time. And once we eliminate a variable, then we just have a system of two variables with two equations. Alright, so this I'm going to call equation 1, this I'm going to call equation 2, that I'm going to call equation 3. Alright, so if I take equation 1 and add it to equation 2, alright, these x's will cancel out, and then -2y plus 3y would just be y, and then 3z plus nothing is just 3z, and then 9 plus -4 is 5. So that's one equation. Now, a new equation that has only two variables. Alright, so now I'm going to take equation 2 and double it. So multiply everything in equation 2 by 2 so that I can add it to equation 3. And then what happens there is my x's get eliminated. Alright, so if I double that first term and add it to 2x, they cancel out. If I double that 3y, I get 6y, add it to -5y, and I just get y. Alright, if I double 0, it's still 0, plus 5z, so that just becomes 5z. And if I double -4, I get -8, add it to 17, and I get 9. Alright, so now I have this new system of two equations with two variables. Alright, so now I could just eliminate my y's because they just have a y and a y. So now if I take everything in this bottom equation and multiply it by -1 to get opposite coefficients, and then add, now my y's cancel out. Alright, 3z plus -5z is -2z. 5 plus -9 is -4. Alright, and now I could divide by -2, and I get z is equal to 2. And then it's kind of in triangular form now. I have that one equation with one variable. I could take this equation and now replace z with 2, and I get y plus 3 times 2 is 6 equals 5. So I get y is -1. Alright, then I could plug in these two into the top equation and solve for x, or any of the original equations. So like x minus 2 times -1 plus 3 times 2 equals 9. Alright, that we get that same equation that we did earlier, x plus 2 plus 6 equals 9, which implies that x is equal to 1. And there's our solution. Alright, and that's how we're going to solve a system of three variables, by doing elimination. Alright, and our final answer could be written as an ordered triple. And you could check it by plugging it back into all three original equations and seeing if it works. You can also just use the calculator to solve it, but you should know how to do this by hand.